Okay, first of all, I would like to thank the Fundación Contra la Hipertensión Pulmonar for the kind invitation to participate in this symposium. And I'm going to talk to you about the physiological and pathological role of potassium channels in pulmonary arterial hypertension. So during the first slides, I'm going to talk to you about their physiological role of PAH. But there are a number of processes that are involved in the development of pulmonary arterial hypertension, including the metabolic shift, inflammation, endothelial dysfunction, and also ionic remodeling. And this ionic remodeling means essentially an impairment in the potassium channel activity, which happens essentially in those myocytes present in the pulmonary arterial vessels. Now, let me, with this simple picture, let me give you an idea of why potassium channels are important in the regulation of vascular tone, of pulmonary vascular tone. Well, pulmonary potassium channels play a key role in controlling membrane potential. So when the potassium channel's activity is normal, the potassium efflux goes from the inside to the outside of the cells, and this permits or drives to a membrane potential levels, physiological levels of about -60 to -40 millivolts. Under these membrane potential levels, the cells are hyperpolarized, so there's a reduced calcium entry, and that leads to vasodilations. The arteries are relaxed. On the opposite, when there's an impairment in the potassium channel activity, or there's a decrease in the potassium channel expression, that leads to an increase in positive charges, in potassium ions inside the cell, leading to membrane hyperpolarization, which induces the activation of a number of mechanisms, especially the activation of voltage-dependent calcium channels, leading to an increase in intracellular calcium and vasoconstriction. The same can be said for other important processes in pulmonary hypertension, including proliferation. Now, so very basic message will be that as the potassium channel activity is reduced, that turns the membrane potential in these myocytes more positive, and that enhances pulmonary arterial contraction and proliferation. And therefore, that leads or is important in the development of diseases, including pulmonary arterial hypertension. Now, what potassium channels are important in the pulmonary vasculature? Well, here you can see the superfamily of ionic channels, and in red, there are represented the potassium channels, which, as you can see, they account for essentially half of the ion channels expressed in the human genome. So many of them are expressed in the pulmonary vasculature, but unfortunately I don't have time enough, so I will just focus on some of them that we have more evidence in their role in the pulmonary vasculature and in the pathophysiological role in pulmonary arterial hypertension. So one of these families is voltage-dependent potassium channels, which includes, as you can see, a lot of different members. And a potassium channel, just to remind you, are composed of the association of several proteins. In KV channels are conformed by the association of 4 alpha subunits, which lead on a pore between, and that is where potassium channels are flow. So the classic technique to record potassium channel activity is the patch clamp technique. Here you can see isolated myocyte, and we can control the activity, we can record the potassium channel activity by applying a number of different protocols, changing the membrane potential and then recording the potassium currents, as you can see here, under control conditions or under the exposure of different drugs. And we can characterize which potassium channel is important in a particular myocyte by using selective drugs like Dpto, which is a Kv 1.5 channel inhibitor, and this can give us an idea of that most of the current in the pulmonary arterial smooth muscle cells is triggered by Kv 1.5 channels. Now, one important feature in the pulmonary arterial smooth muscle cells, if we compare with smooth muscle cells from systemic vessels, is that, as you can see, the potassium current is markedly increased in the pulmonary arterial smooth muscle cell. And why is this for? We don't know. We don't know, but as I have mentioned to you previously, the KV channel activity prevents an excessive depolarization. So this may be like a protective mechanism that the pulmonary artery smooth muscle cells have in comparison with smooth muscle cells from other vessels, from systemic vessels. So this increased potassium channel activity in pulmonary arterial smooth muscle cells may even contribute to the lower pulmonary arterial pressure, characteristic of the pulmonary vasculature in comparison with the high blood pressure typical from the systemic circulation. Now, in previous studies, we have found that potassium channels represent a target of many vasoactive factors, including vasoconstrictors and vasodilators. And here I'm going to show you some examples, like thromboxane A2 and serotonin. Both of them are important pulmonary vasoconstrictors, and we found that both vasoconstrictors inhibit the potassium channels, reduce these currents, and lead to membrane depolarization, increasing intracellular calcium, and vasoconstriction. And the same can be said for vasodilators, but in the opposite way. So vasodilators can increase the activity of potassium channels, and here I show you an example. There are many examples, nitric oxide, prostacyclins, etc. And here I show you an example of riociguat, a drug used for the treatment of pulmonary arterial hypertension. Here you can see potassium current recovered by applying a depolarizing pulse, and how riociguat increases the amplitude of this current. And this leads to a membrane hyperpolarization and relaxation, which can be prevented, inhibited by the inhibition of a specific potassium channels, Kv7 in this case. So basically, this is one of the message I would like to tell you, that potassium channels represent a common target for both vasodilators and vasoconstrictors. Now, what about the pathophysiological role? Well, there are a lot of evidences in favor of a role of potassium channel impairment in the development of pulmonary arterial hypertension. In fact, the attenuated expression or activity of potassium channels, including especially Kv1.5 channels and TAS channels, have been observed in a variety, in a great number of studies, both clinical and experimental. And this is an example. My colleague Paco showed you before about the model, the most characteristic model of pulmonary arterial hypertension that involves the addition of the VEGF antagonist and the exposure to hypoxia. These animals, as he mentioned, develop pulmonary arterial hypertension. Here you can see the pulmonary arterial hypertension levels in a normoxic animal or in the pulmonary arterial hypertension animals. And these animals are, they have a marked reduce of the potassium channels as presented here. The activity is much reduced. This can be represented, and this inhibition of this reduced activity of potassium channels induces membrane hyperpolarization and makes these arteries more prone to contract and to proliferate. Okay. 2 minutes, okay. So, well, then I'm going to skip this one. It's just the message is just to tell you that it's important to know the mechanisms involved in the development of this impairment so that we can look for alternatives to prevent it. In this case, we saw some beneficial effects with an antagonist, which was able to restore part of this impairment. But for sure, the confirmation of the role of potassium channels in pulmonary arterial hypertension is the identification of mutations in some particular potassium channels. So as it has been mentioned before, KCNK3, which encodes for TASC1 channels, was the first channelopathy discovered. And then here I'm going to show you that channelopathy was associated with a marked reduction in the currents induced by this particular channel. Importantly, some of this impaired activity could be partly rescued by one drug, the ONO-RS-82, which is a phospholipase 2 inhibitor, but in some others it couldn't. Here, in collaboration with Professor Alistair Mathieu from the University of Kent, we collaborate with him to characterize two novel mutations in the Spanish cohort. Here you can see that those two mutations were associated with a total loss of function of the TAS1 channel, and unfortunately they could not be rescued by the phospholipase A2 inhibitor. Now, in the last year, additional potassium channels have been demonstrated, identified that there are mutations in some other potassium channels, like KCNA4 and ABCC8. I'm not going to talk to you because I don't have time about the ABCC8, which encodes for a SUR1 subunit of the KTP channel. But we are now in collaboration with other members of people present in the room that I will mention later. We are trying to functionally characterize some novel mutations in the KCNA5 gene from a Spanish cohort. There were 10 mutations. We are trying to, we're skipping some of them, but we are trying to deep in the characterization of some of them that are localized here. You can see here the locations of the different mutations, and we have some preliminary data. Here is the current, the Kb1.5 current in cells transfected with the wild type KCNA5 and with the different mutations. As I mentioned, it's just preliminary data. In some cases, we just have like 2 or 3 experiments, but some of them, as you can see here, this substitution of arginine by proline, we see a marked attenuation of the current, which probably explains that these channels are not functional. And well, we have a lot of way to go, and I don't have more time, so I just would like to thank all the members of my group, especially Gemma Mondejar, who has performed many of the experiments that I have shown you, and also I would like to thank some of our collaborators from Hospital 12 de Octubre, Pilar Escribano, Jair Tenor y Pablo Lapuncina from Hospital La Paz, I'm Mauro Lago, I'm Diana Valverde from Universidad de Vigo, and Teresa González and Carmen Valenzuela from the EB. Thanks a lot.
Thank you, Ángel. It's time for questions. Ángel, aunque sean datos preliminares, mostrabas que 2 de las variantes que hemos detectado y que estabais validando funcionalmente, en vez de reducir la corriente, lo que hacen es un incremento de la corriente.
Bueno,
sí, por lo que se ve ahí.
Es la sensación, lo que pasa es que todavía no nos podemos, no podemos asegurar que están aumentando la corriente. Lo primero porque es un dato de 2 o 3 experimentos. Hay que tener en cuenta que estos son células transfectadas y muchas veces también la dependencia de cómo se está haciendo esa transfección puede variar la corriente total. Por otro lado, solo medir la corriente total no nos da toda la idea. Hay que ver otras cinéticas de si se están, no solo si se abren los canales, si se abren con la rapidez que deberían, si se cierran cuando se deberían cerrar, se inactivan, etcétera, que eso es lo que conlleva todavía. Entonces, por eso simplemente os he puesto que son datos preliminares, pero no me aventuro a decir que estos canales tengan más corriente. O pueden tenerla y, sin embargo, que al ensamblarse con subunidades reguladoras hay alguna alteración final de la actividad. O sea, que no es tan sencillo.
If I may, two quick questions. One, in terms of the different mutations that you're observing, I mean, some of these look like some of these look like real dominant negative mutations, that they are really completely abrogating function.
Like this one.
Yeah. And yet there's obviously heterogeneity around that. So that, and the implication there is, those dominant negatives probably are not going to respond to some of the therapeutic interventions.
Well, as you say, probably we have to deep on that, because I mean, we don't really know what this means yet.
Yeah.
We first want to know if that means that the channel is not trafficking to the membrane, for instance, and why it's not trafficking. Sure. If we know the reason, maybe we can revert it.
Yeah. I mean, it just amplifies the notion that when we talk about precision medicine, it's not just at a gene level; it's the allele that's going to be pretty important, the specific type of mutation that's going to be important. The second question really is, as you showed us and reminded us, this incredible array of the family of potassium and channels in general, and the opportunity to recognize there must be redundancy amongst those channels, and the opportunity to exacerbate function of other members of channels is clearly an opportunity.
Yeah,
to explore.
I agree, and that maybe can explain why some person have the mutation but do not develop the disease, but others do, because maybe there's some redundancy, of course.
Yeah. Just to add to the Angel's comment, one of the variants that we have detected, KCNA5, has been already functionally tested to abrogate the function of the protein, and in this family there is also a pathogenic stop variant in BMPR2. So it's kind of explain how this can explain in part which is the low penetrance, and these kind of variants can add for that.